2 out of 3 days and make everybody crazy at that time and depressed too. You know, whenever we had the old movies about depressed scenery, they always come to Geelong and make those old movies, sad movies. But no longer. You see all these light drizzles, which although depressing, actually is very beneficial to the agricultural industry. But they're pretty much gone. In fact, not only right here is decreased. In Southwest, to begin with, they get very, very little light drizzle in the winter and spring, and now the decrease is even greater in terms of percentage, and that contributes to the almost yearly, every year we have a spring drought in the Southwest, and no one can plant their rice field. So this effect to Taiwan is really we have already seen, and that's not at all surprising. This 1 degree would change that much, and over the last say 50 years, there's like a 0.6 degrees change. So 0.6 times 140% essentially is close to 100%. So 100 factor of 2 increase here, and essentially factor of 2 decrease here already happening in Taiwan. That I already said. For southern China, we also did similar analysis, and the change is not as drastic, and top 10% still. Taiwan 143%, here is close to 60% southern China, and also similar decrease in light precipitation. And when you think about this result, actually, I want to go back to the Japanese data. I mean, they show very consistently with what happening in Taiwan and in southern China. I mean, except that at that time they did not tie to temperature change. I mean, we know the last 100 years or so, temperature increased by like 0.7 degrees, 0.7 degree, and when you divide 40% by 0.7, it's fairly large. It's about 60% decrease per degree, and that's very much in agreement with our result. So our result is really not surprising until we showed that for global data we also get a really large effect. This global data, top 10% increase by close to 90% for each degree. And in comparison to current, to 2007 IPCC's climate model shown in blue, which is summarized by Sun et al.'s paper, and the shape look beautiful. I mean, the red is what I just showed our analysis for global data. This is global precipitation climatology program data. And the average increase in precipitation intensity is 23%. Remember, the 7% per degree hypothesis here we are showing is actually much more, 3 times more than 7%, 23%. And the top one is more than 90%. And also with relatively robust, relatively small 1 standard deviation. But when we publish the result and compared with climate model, those models for IPCC 2007, they should, like I said, the shape look beautifully in agreement. but the value is very different. The red is scale here, the blue scale is exactly 10 per, factor of 10 lower. So the climate model way under-predicted the change. So that means we had to conclude in that paper that a climate model seriously underestimate the risk of flood and mudslide due to the change in precipitation extremes. And as a result, right now, most of these climate modeler, they don't believe our result. And but I think our result is correct. I got to 20-some minutes. That's okay. Because a lot of people didn't believe what we showed in the paper, and also we also realized there are certain shortcomings in the GPCP data. And that has to do with GPCP data is 1970, only about 30 years worth of data, and spatial resolution very coarse, shown here, and also many different satellite data going into GPCP compilation, and that means different calibration, different bias. So we decided to make a check of the GPCP data by looking into the NSAP and NCAR. NSAP is US NOAA's weather center, and also European weather centers, so-called reanalysis. Their reanalysis is much longer in time. It goes all the way to 1950s. And their reanalysis, although they use observations for reanalysis, but they don't use directly the observations for precipitation. Instead, they calculate their precipitation by using observed moisture and observed wind field. So in that sense, it's an objective evaluation of the GPCP result. And here is their result. Again, the yellow one is what we got from GPCP, and the blue one is I just showed for the models. And the blue using this scale, the yellow and other two using this scale. And the two reanalysis, they look like a little bit lower compared to ours. But when you look at the shape, overall shape, except the top one, they are not only shape but also value relatively close to each other. In fact, the average precipitation intensity change for these two reanalysis is within like 20% with the GPCP data. Essentially, these reanalysis is still close to factor of 10 higher than the models. So that means there's generally agreement from reanalysis with direct observation, and so that means the direct observation what we derived is credible, and what's wrong must be climate models. And we believe they underestimate the reason they underestimate the change is simply because they don't have the resolution, the spatial resolution to do the convection, to resolve the convection. Of course, you might want to ask the question because you know these reanalysis, their spatial resolution are, this is 2 degree by 2 degree, that's 200 meter, 200 kilometer by 200 kilometer, 100 kilometer by 100 kilometer. They are also very poor, but the point is although their resolution is not enough, they do have observed moisture and wind field. In that sense, they can get the result for the convections. Another criticism of what we did is that our data was too short, and of course we have no way to increase the time of data. Observation is global observation of precipitation it's only available since the satellite time. So it's not. But we can look at the long time model change and see if there's a nonlinear effect here. And it turns out that we can do every 10 years, every 20 years, every 30 years, and we can also check for this model for those years that's greater than 70 years. 70 years, you can see here is this one, and 30 years, and that's close to GPCP data. It's only a little bit greater, and in fact, these two values are within 1 standard deviation of the combined. So I'm pretty sure this says that the time shortage, short time for data is not a serious problem in getting the different value. Finally, with the doubt for the analysis and also the data out of the way, we applied our analysis for those areas affected strongly by tropical cyclones. Shown here in red lines, they are tropical cyclone tracks covering 25 years from 1981 to 2005, and of course Northwest Pacific is the typhoon has the most in the world, and Taiwan, because the track pass over Taiwan so frequently, you don't even see. Even Japan is hard to see. Actually, you don't see Japan either. Maybe so here. Korea here, and we analyze. We do our analysis for all these rectangles and see how the precipitation has been changing. Here we show also the 10 beams. This is top 10% precipitation. We add 2 categories. This 11th beam is top 5% heavy precipitation. That's top 1% heavy precipitation. And for those areas affected by tropical cyclones, you can see the top 1% heavy precipitation increased by about 225% for just 1 single degree in global temperature increase. And I don't need to remind you what the result is going to be. That's really says what we have seen in the past 10 years, tragic flooding and mudslides. had to do with this type of effect. And again, I show Taiwan and repeat, I mean, it's very, this is 140% compared to global is, Taiwan actually a little bit more than global, 125% for this top 10% precipitation, but consistent. So with that, I conclude. Make my conclusion, the top 10% heavy precipitation of tropical cyclones landing in Taiwan showed an increase of about 100% in the last 40 years. And similar change, in fact, and more so, are found for other regions affected by tropical cyclones. In fact, Philippines, if anybody look at what happened to Philippines. In fact, we proposed to the Philippines scientists to analyze their typhoon change several years ago. Still, there's no response yet. The third point I want to make is that this is already happening, 100% increase already happening in Taiwan. And the temperature is, global temperature is going to increase again due to global warming. And it's going to be another 100% in about 30 years or so. And yet, atmospheric CO2 reduction by reducing the emission will take at least 50 years to be effective. That's simply because what already in the atmosphere, the CO2 already emitted, their lifetime is so long, it's longer, it's close to 100 years. So the increase further increase in heavy precipitation is inevitable in the next 50 years. Therefore, I think for Taiwan, it's really we need to hurry up to do the adaptive action. And in fact, I talked a lot to the Taiwan government and news media too, but I get very little response. They also thought what I said maybe exaggerate, but I guarantee you it's not. And I hope that my colleagues in these mainstream meteorologists in our Central Weather Bureau would someday come into agreement that we really need the government to come up with actions to do preventive to build up preventive facilities for flood and also for drought. And one thing before I close, I want to say is sadly enough, only 2 weeks ago was the I think 2-year anniversary of the village we call Shaw Chen Liu village that was covered by mud in 10 seconds in Morocco typhoon. And more than 400 people lost their lives. And yet, the people who live around there demand the government to rebuild their village around there again. And the government agreed. And I have no, I keep saying that that's not the way. You just put these, and also that's morally morality is very bad because these are Aborigine people, you know. And although these people, they say, we love to live in the mountains. That's our traditional home. And the government say, oh yes, we'll rebuild the home for them. But the thing is, they don't know their home is no longer safe. But the government has agreed to send them right back where they are. And you know, I don't know what to say. Except I said many times during the news media interview, I said Aborigine people, although traditionally they live in the mountain, but if you look only a few hundred years back, they actually live in the plain. It's because of the Han people who moved into the plain. They kicked them into the mountains. You know, they drove them into the mountains. And so they really traditionally are not, they didn't live in the mountain. They are not that dumb because there were a lot of mudslides even way back. But anyway, let me end my talk here and thank you very much.
Thanks to Professor Liu. Now we still have some minutes left. Any question? Okay, please.
So you mentioned the main cause of the increasing trend of heavy, high-intensity precipitation, tropical cycle. But I'm curious about the cause of decreasing trend of so low precipitation or moderate.
Well, first of all, I want to say, I say the reason this heavy precipitation increasing is not because of typhoon. It's because of typhoon affected by the global warming. Okay, and the reason for decrease in moderate and light precipitation is the same. When you need, because of these big convection like typhoon, when their intensity, you know, increase due to global warming, they pump a lot of energy from the surface or heat from the surface to the upper troposphere, making upper troposphere more warmer. And when you have a warm upper troposphere, you have a relatively smaller so-called lapse rate, or you have an inversion. Okay, global. This is a global inversion, and that means that the atmosphere got more stable, and therefore the light and moderate precipitation, they need instability to come down. They decrease. That's the reason.
How about the behavior of a thunderstorm or normal synoptic scale low system?
Yeah, that's a very good question. Thunderstorms, of course, is one of the what I call the heavy precipitation category. Heavy precipitation category. The number of the frequency would increase because they are the driving force. But at the same time, once you start this a while, you also, it's a self-constrained type of action. That's why people say total number of tropical cyclones should be decreasing. But right now, we just don't have very good data.
According to the physics, the conservation of energy law is still valid. And of course, if it doesn't conservate, means that you need to find some another form of energy transfer from one form to another form, and just to get again balance. So in this case, just to prove all that stuff, I'm not, of course, from this area, and I'm not very much familiar with the detailed information of all the things you covered by your presentation. I would like to see the data from South America, for example, detailed data about that. Detailed data from the South Africa, from the southern part of Australia. And maybe there you have the different following of the all that data which you have demonstrated here. I'm just guessing. I'm just would like to be absolutely clear picture done here about different other regions. Maybe we have inverse situation in a southern part of the globe. Because when you say global warming, global law, global process, it means that it should be different conditions done, data from the northern part of the world and the southern part of the world, and mixed up together, and to see that the conservation law is in troubles.
Yes, your question is, I don't have a figure showing the global temperature change. Indeed, as you said, we usually observe the temperature increase in the northern hemisphere tend to be somewhat higher than the southern hemisphere. And also because the southern hemisphere has more ocean, we also know that land mass increase, the temperature increase is higher than over the ocean. Nevertheless, the southern hemisphere, the temperature increase in the last 100 years is only about, say, in the north, maybe 0.7, in the south is like 0.6. It's not, yeah, it's not a large change. And the precipitation, we found, say, for at least for the ocean area below, I mean, not high latitude. High latitude is hard to say. Below 60 degrees, the change in precipitation in the southern hemisphere, over the oceans especially, compared to the northern hemisphere, is relatively consistent.
Just a question about the climate in the past, because you said that we are seeing a 1 degree increase, but in the very distant past, there is evidence that the Earth was at more than 5 degrees 5 degrees Celsius more than now. So the weather was what type of weather they had in the past?
Okay, you are talking about during the dinosaur years.
No, that's the dinosaur, but a few million years ago, of course.
Yeah, well, it has to be. I mean, 5 degrees warmer than now. It really pushed back to about at least 60 million years ago. That's when the temperature really high. And from what I believe, we haven't run the model like that, but I believe during the dinosaur years, when temperature was at least 5 degrees higher, I'm pretty sure the heavy precipitation is probably 10 times current ones. That's my personal belief.
If the trends that you're showing show this vast and sharp increase in precipitation with the heavy storms, and the trend is very steep, what happens in 50, 100, 200 years from now?
That's very, very, very good question. I don't want to see that.
It'll all be.
I'm glad I won't be able to see that.
But I mean, doesn't this lead to the conclusion at some point in the future that all the precipitation will be in one gigantic typhoon for the whole world?
No,
Not that drastic.
No, not drastic. But you know, the heavy ones. You see, what do we show is top 10%, top 5%. You still got a lot of other, but nevertheless, I think the writing is on the wall. I think it's highly unlikely to see anything changing this type of change in the future. I'm pretty sure these are continue going to increase. But by the way, you see, globally, strangely, actually, I don't understand why this little one has a little bit increase, but statistically, it's not very significant. But here, you see, their decrease is not that large, and you still will get some light precipitation in the future.
But this trend, the overall trend with time, these trends continue to change, increase, yes?
Yes.
Decreasing here, increasing there.
Yes. That won't change.
That
that
sounds cataclysmic.
But just taking into account that the world does exist more than 6 billion years, it should be some balancing process which will return back. And what you have in your mind, what kind of process can return back the normal process of precipitation, just to be sure that the world is not in danger?
Oh, okay. First, I want to make this clear. If you look at the total precipitation, when you add together, it changes very little. This is increased by 100-some%, but you see here, many of them around 30% or so. When you add them together, they are actually, the total precipitation doesn't change very much. In fact, we analyze it using same method. For total precipitation, for each degree, you add all 10 beans together. The increase is only like 2 to 3% per degree. So temperature increase at the end of this century, say the maxima, they talk about 4 degrees. That would mean total precipitation increased by 2 times 4, close to 10%. Okay, total precipitation increased by 10%. But the extremes one, the heavy one, up 10%, is going to increase much more.
And asking about physics, just what kind of process will return back? What kind of process goes up and down?
Yeah, I'm sorry, I'm answering the
but
previous
this
question
equation.
and this one. What turns back, I think what turns this way is global warming, and if we want to turn back, we got to cool it.
What causes global warming?
Okay. That will take some time to do. I know a lot of people. In fact, my meteorology friends, they have a reservation about CO2 or greenhouse gas cause global warming. I believe it's mostly caused by greenhouse gas increase. A lot of people don't believe it, but I think the probability is very good that it is correct that greenhouse gases cause global warming.
Okay, because time is limited, and I will still have a break later. So if there's any more questions, we can discuss during the break. Thank you.
Thank you, Dr. Liu, for your intelligent answers. We would like to welcome the chairman, Dr. Lee, on behalf to present the memorial trophy.